This is section 5.2 where we talk about observational studies versus experiments. I don't usually go over these comics, but this is one of my favorites. Okay, A labeled it correlation. In our class, we're calling it association. Because it says 100% of people who breathe die, which is true, everyone who breathes eventually will die. Okay, but that is different from causation, which says 100% of people who don't breathe die. That actually is cause and effect. Whereas the first one, that's just an association. Well, let's start off here where we compare two groups. How would we determine if a new anxiety medicine is effective? What we're going to want to do for something like that is use a method of comparison. Okay, we want to use two or more groups where we'll have a treatment group and a control group. So the treatment group would be like they get the medicine. And the control group would people who don't get the medicine. Because you can't just give everyone in your the anxiety medicine and wait to see if they get better, because maybe they would have just gotten better anyways. So what you have to do is you have to have some people that have the medicine and some people that don't have the medicine, so you can compare the difference between the two groups. So what would be the explanatory variable here? An explanatory variable is usually going to be our grouping variable, like what group we put them in. So this would be whether or not they get the medicine. And then when we talk about what is the response variable, what are we actually measuring? Like what do we want to study? That would be their anxiety levels. Did their anxiety get better? So we'll just put anxiety levels. Then we would compare the two groups' responses to the explanatory variable. So we're comparing their anxiety, the anxiety levels, and we're comparing it based on whether or not they get the medicine. Which is a yes or no. And we hope to conclude that any differences were just due to the actual medicine. So when our treatment and control groups are similar, we want similar groups apart from the actual treatment, then the difference in any responses is likely due to the actual treatment. So as long as our two groups are similar, if one group has much lower anxiety, hopefully the group on the medicine, if our medicine group has much lower anxiety levels, that probably means that it was because of the medicine. So there's a few things we need to learn here, such as the difference between observational studies and experiments. So we could just survey people on the new medicine and people not on the medicine and see which group has lower anxiety. This is called an observational study. Okay. It's an observational study because the people chose whether or not they took the medicine. The researchers are just observing passively. We're not controlling anything. We're not intervening. We're not making people take the medicine. We're just watching people do what they want to do. So the better way to do this is we could actually find people to be in a study, and then we'd randomly assign half the people to take our new medicine and half the people to not take the medicine. This is what we call a controlled experiment, because the investigators are imposing the treatment. So we are actually making people take the medicine and not take the medicine, not in a mean way. Obviously, they've signed up to take the medicine. Okay, the group that gets the medicine is called the treatment group, and the group that doesn't get the medicine is called a control group. Okay. We call it a control group because it lets us kind of control our experiment. We're comparing everything to it. Okay. But the key thing with an experiment, we will ask you on your homework, is this an experiment or an observational study? So an experiment, we put people into the groups. We make the people take the medicine. An observational study, we just let them do what they want and we just watch them. We don't do anything to the people in an observational study. Now, if two groups are different with respect to something other than just the treatment, we say that's a confounding variable. So a confounding variable we talked about in the last section a little bit. So the confounding variable affects our response variable. It makes it so we can't tell whether it's the medicine or a confounding variable affecting our anxiety levels. So some examples would be like if the treatment group happens to just be younger than the control group, then age would be a confounding variable. Or if the treatment group was healthier than the control group before the study starts, then initial health would be a confounding variable. Or if the treatment group has higher socioeconomic status than the control group, then that would be a confounding variable. So observational studies have a lot more issues with confounding variables than experiments do. We cannot say cause and effect from an observational study. We can try to control for some confounding variables using statistical techniques after we actually collect the data, but we can't really eliminate their effect. Okay? And so we just don't trust observational studies as much as we do experiments. Okay. But in a well-designed, and that's key, there are a lot of experiments that are not well-designed, but in a well-designed experiment, hopefully our two groups are similar with respect to possible confounding variables. And if our two groups are similar, we can then mitigate the effects of the confounding variables. And this allows us to cautiously show cause and effect. I say cautiously because any experiment, we can still get unlucky. We can still just pick weird samples. We can have things that we didn't expect show up. Okay. But if it's well designed and we get these results that show cause and effect, it's probably true. Now, past that, we will like to double check. We want other people to run similar studies, okay, but we can cautiously say cause and effect. Okay. And as a note, in an observational study, we call the individual people or items observational units, which we've been using that term this semester. But in an experiment, we call the individual people or items experimental units. Now, if you forget and write the wrong one on your homework, that's not going to matter at all, okay? But I didn't want you to be surprised when you saw that new term of experimental units. So to review, in an experiment, the investigators or experimenters, researchers, whatever you want to call them, control who is in each group. Okay? In an observational study, the researchers only observe. They don't control who gets the treatment. If we want to show cause and effect, we must have an experiment. So what are some elements of effective experimental design? We said we want a well-designed experiment. So here are some things we needed to take into account. First one is randomization. So we want to randomly assign subjects to the two groups, and that will ensure that the two groups are alike. So the two groups. So when we randomly assign people to groups, that tends to balance out all the other variables between the groups, all those possible confounding variables. So any variables that could have an effect on the response should be equalized in the random assignment between the two groups, and therefore they shouldn't be confounding variables. When our groups are randomized, we select what group they're in by means of some chance mechanism we want to make actually random, so like coin tossing, computer-generated random numbers. Randomization reduces human bias because people don't decide who gets the treatment. So one thing that we found happens a lot, like one example, is if physicians get to choose who will get a surgery, they may, consciously or subconsciously, put the healthier patients into a surgery group because they're healthy enough to undergo surgery. In a randomized study, we just make sure that everyone's healthy enough to undergo surgery before we start. And so once we know that we start with healthy patients, then we randomly put half in surgery and half in the control group. We can't randomize observational studies because we don't have any control. We can't actually make people go in the group, so you can't actually randomize it. Okay, but we should always randomize controlled experiments. Unfortunately, not every experiment out there is well designed and randomized. You should always check before you trust the results. Let's see, blindness. If subjects know which group they're in, they might react to the idea of the treatment instead of reacting to the actual treatment. So it's good to have a blind experiment, meaning that subjects don't know which group they are in. Okay. A note here, so if a person's subconscious belief affects their physical health, it's called psychosomatic, if you see that term. So we don't want patients to know if they're actually getting the treatment or not. Now, if investigators know which group the subjects are in, they might treat the groups differently. Okay. Sometimes they also assess the outcomes differently. So if they know that someone's getting the actual medicine, they might be more likely to tell them that, yes, it's safe for you to go exercise, or it's safe for you to go out in public, things like that. Whereas if they know that maybe they're getting the placebo, they might tell those patients to be more cautious. Okay. Also, when they assess the outcomes differently, if they know that someone's getting the surgery, like they might expect them to be doing better, so they might make their scores just a little bit more positive. So we want what's called a double-blind experiment. That means neither the subjects or the people who interact with them know which group they're in. So in a double-blind experiment, neither the subjects or examiners know who has received the treatment. So a placebo is what we actually use to make our study be blind. So a placebo is a neutral treatment, such as a sugar pill or a saline injection. This is used to avoid possible psychological effects that arise when a subject knows whether or not he has received the treatment. So placebos help the study be blind. That's what we have to use to make a blind study. Interestingly, we found that big, colorful placebos work better. Apparently, people probably think it's the actual drug if it's big and colorful. If subjects still figure out which group they're in, even though we give them placebo, we say they broke the blind, okay, and we might not get good results from them. Okay, so replication here, we mentioned this. We don't like to trust just one study or experiment. We like to look at the results of a lot of similar studies and see if the results are replicated across those different studies. So examples of the placebo effect. The placebo effect is when people's symptoms improve because they think they're getting treatment, but in fact, they aren't getting any treatment. So one study gave one group of people crackers and told them they were super healthy crackers carefully designed to give them energy without spiking their blood sugar. And they gave another group of people the same crackers and told them they were just delicious junk food. The researchers then measured the blood sugar of both groups. The group that had been told the crackers were healthy had lower blood sugar levels. So what happened here? It was the placebo effect. If they think that the crackers are healthy, their body responds differently, and to their body, those crackers were healthier. Okay. Or they had another study, and there is just study after study showing that the placebo effect works. Okay. So in one study, well-trained competitive cyclists were told they would receive either a zero dose of caffeine, or a low dose of caffeine, or a high dose of caffeine before a time trial, but really they were all actually given a placebo. So the athletes who thought they were getting a small dose performed 1.5% better than the ones told they didn't get any caffeine. And the high dose group showed an increase of power of 3% over the 6-mile race. And it says here 6% doesn't sound like a lot, but to these athletes, that was a really big deal. So there's an article with lots of examples of the placebo effect. Well, if experiments are so good, why don't we always do experiments? Okay, because as we said, if the treatment and control groups are similar, apart from the treatment, then a difference in responses is likely the effect of the treatment. So a well-designed, randomized, controlled, double-blind experiment can show a treatment causes, it can show that cause and effect, causes a response. But we can't always do a well-designed experiment. So some reasons why is that good placebos can be hard to find. So for example, if your experiment is to see if surgery helps with back pain, it's pretty hard to fake a back surgery for the control group. Okay, so they know if they got surgery or not. You can't always do an experiment. Sometimes we can't find people willing to be in the experiment. Okay, or sometimes we can't actually make people be in certain groups. Like you can't make some people be from Iowa and some people be from Utah. Okay, and so all you can do is just observe the people that are already from Iowa and some people from Utah if you want to compare something between those two groups. Okay. Sometimes a control group isn't ethical. So like if our experiment is to see if a new treatment helps with a severe illness and the control group doesn't get treatment, then the people in the control group could die. So it's not fair to give one group treatment if they need it. And sometimes imposing the treatment isn't ethical. So suppose we want to see if smoking causes lung cancer. We can't assign some people to smoke and some people not to smoke. It's unethical to make people smoke. Okay, that's why our data on smoking and lung cancer comes from observational studies. However, we have done enough observational studies over the years and controlled for possible confounding factors in other ways. And so we are convinced that we can say that smoking causes lung cancer. But when we have these observational studies, it takes years and years of repeated observational study after observational study before we could ever get to the point that we could say cause and effect. So let's summarize here. When we have a controlled experiment, that means researchers decide which subjects are in the treatment and control groups, hopefully randomly. An observational study is subjects assign themselves to the different groups, usually by their own choices or behavior or characteristic or just like the way they were born. Okay. Controlled experiment, researchers impose some treatment or non-treatment on the participants, like we're doing something to them. But an observational study, we just passively observe them, we just collect data on them, we don't do anything to them. Okay. Now, notice this one looks exactly the same no matter what you're on. So random samples let us generalize our results from the sample to the population. And that's true whether it's a controlled experiment or an observational study. And we'll talk about that in a second. Let's see, for a controlled experiment, confounding variables can be controlled for if randomization is used. So we don't have to worry about those confounding variables. But for an observational study, the confounding variables, we can maybe control for them after we collect the data using some techniques, but not very well, and we can't always do that. And let's see, well-designed experiments with random assignment can allow us to cautiously infer cause and effect, causation. But for an observational study, do not imply causation unless multiple studies over a long period of time all give the same result. And even then, be careful. So let's talk about generalizing in cause and effect again. So sampling is how you select the units, the people or items to be in your study. So you want to use a random sample so that your sample is representative of the population. Representative means that our sample is similar to our population. That means we can generalize our conclusions about the sample back to the population. We can be like, oh, if our sample is like our population, then whatever results I find for the sample probably also apply to the population. Now, so that's sampling. That is different from assignment. These are two different things. They seem kind of similar, but they're two different things. Assignment is how you divide up the units of people into your explanatory variable groups. So random assignment means we randomly assign the subjects to the groups in the experiment. Random assignment means our groups are likely to be similar to each other. And if our groups are similar to each other, then we can mitigate the effects of confounding variables, and that means we can claim possible cause and effect. So, in summary, if you want to generalize the results of your sample back to the population, you must pick a random sample of people to be in your study or experiment. Okay. And you want to make sure the random sample comes from the population you're interested in. So if I'm interested in all adults in the US, I need to make sure my random sample comes from all adults in the US. I don't want to just pick a sample of adults from Utah, because if I only take a sample of adults from Utah, I can only generalize my results to Utah. Okay. And if you want to cautiously show cause and effect, you must use an experiment and randomly assign people to the groups in your experiment. So this is blocking. We don't expect you to really know how to do blocking. We don't expect you to know how to analyze your data differently, but we want you to know that it's a possibility. Okay. So for this example, did you know that anxiety medicines often affect men and women differently? So if we want to compare two anxiety medicines to see which one was more effective, then gender could be a confounding variable. So we know that randomly assigning people into our two groups will help reduce the confounding variables most of the time. But does it work for every experiment? So we're going to go use an ISI applet. So I come to that applet, I go to the exploring randomness and randomizing subjects. So in this subject, what happens if you look over here, these are 24 people and they're getting divided into group 1 and group 2. Okay. There are 8 females, those are the ones that are kind of a slight pink or red, and the males are all the ones that are blue. So I can ask this applet to randomly assign these subjects into the two groups. Okay. So if I hit that, I'll have to take off animate. You can see that group 1 now has, it looks like 8 males and 4 females. And group 2 has 8 males and 4 females. Okay, that's quite convenient. You can see right here, it tells you the names and gender of each people that was in group 1 and the names and gender of everyone that was in group 2. Okay. And it will also tell you that there were 0.667 as a proportion of people that were male in the first group and 0.6667 of the people that were male in the second group. So if I compare these two groups, because I have the same males and females in each group, then gender is no longer going to be a confounding factor. So right here where we say random assignment attempt number 1, we'll say that we had 0.6667 males in the first group and 0.6667 males in the second group. Well, let's try to randomize again. So now we'll randomize again. Okay. And notice my name switched around a little bit. And now I only have 3 females in the first group and 5 females in the second group. So if we look at the proportion males in the first group right here, then it is 0.75 males in the first group, and the second group has 0.5833. So this time, my proportions were not exactly the same, but they are pretty close. And one of the reasons that they're as far off as they are right here is because we have a pretty small sample size. And the difference between like 3 females in one group and 4 females in one group seems like a pretty big proportion here. Okay. If we had a sample size of like 2,000, then having like 1 extra female in either group isn't really going to make a difference. Okay, let's randomize again. Okay, so this time it looks like 1, 2, 3, 4, 5 females were in the first group and 3 females were in the second group. Oh wait, no, sorry, it's 4 and 4. So my proportions of the males are 0.667, 0.667. And I could just keep doing this, and every time I randomize, I get a different one. So this time, notice now there's only 1 female in this first group, or the proportions of males is 0.9167, and the proportion in the other group is 0.4167. So that's quite different. And I could keep randomizing. So look, now we're back to 0.667, so we're even in both groups. Randomize again. Oh, we're still even in both groups. Oh, now we have males are 0.5 in one group, 0.833 in the other group. Okay. And you can keep doing this. Now notice this graph down here. Every time that I do something, it puts the difference in the sample proportions. So someone figured out, well, instead of writing down our proportions in each group, we could just look at the difference of proportions. So if my two groups are the same, the difference in sample proportions would be 0. And so I had a lot of times when I had equal males in each group, so my proportions were the same, so the difference is 0. So let's come back to our notes for a minute. So on my attempt 1, when I had equal proportions in each group, if I subtract those two proportions, I get 0. Okay. For my next attempt, I had 0.75 males in the first group and then 0.5833 males in the second group. So if I subtract that, I get 0.1667. And then my third attempt, I had equal proportions again. So if I subtract them, I get 0. And you can see this table that I made here. I did this 20 times, and I filled in for us the proportion of males in the first group, proportion of males in the second group, and then I even subtracted for you. Okay. So most of the time, you'll see that my proportions are pretty similar in the two groups. Every once in a while, though, I did get something like this one, where I actually had, the first group was all males. Okay. And so that difference was fairly big. But I could just keep randomizing here, and every time I randomize, it adds a different dot. Okay, and notice what happens. Most of the time, my proportions are exactly the same. Sometimes they're a bit different, but as I keep doing it, most of the time my proportions seem to be about the same, which is why my difference is coming out to 0. So just keep randomizing and looking at your proportions of males in each group. You'll notice that they stay fairly similar. Again, the differences you do see are because my sample size is so small. Okay. So again, some of our attempts, most of our attempts, we could probably say like most of our attempts give us similar proportions of males in each group, but some of our attempts don't. Let's ask for 1,000 repetitions and look at the graph of the difference in sample proportions. So I could ask for 1,000 repetitions. And notice, hey, doesn't that look like a normal curve? We see that normal curve everywhere. Okay. You can see that most of our samples had a difference of 0, okay, meaning they were equal. And as we go out, there's less and less samples where the proportions are farther apart. Okay. But most of our proportions are actually, the difference is pretty small, meaning that our proportions in each group were fairly similar. So again, most of the time when we randomize, we'll get similar proportions in each group, so the difference is going to be 0, or at least they'll be fairly similar. But we might get unlucky and get a big difference, such as like attempt number 4, when we had 100% males in one group and only 33% males in the other group. And you just never know what's going to happen when you randomly assign. Okay, however, random assignment usually gives us pretty similar groups, which means usually our confounding factors are controlled for. Now, here's the thing that we wanted to show you. So sometimes if we know in advance that we have a possible confounding variable, we can choose to block on that variable. So in our case, if we know that gender can be a confounding variable, we can choose to separate the males and females in the beginning, and then we make sure we randomly assign 4 females to each group and 8 males to each group. So we first block on gender, we divide them into 2 groups of males and females, and then we randomly assign them into the 2 groups that we actually care about. This way, we're guaranteed to have equal proportions of gender in each group. And we've completely eliminated any chance of gender affecting our results as a confounding variable. So we'll go back to our applet. We'll select randomized block right here. Let's reset everything. Randomized block and go back to 1 repetition. And when I randomize, notice that it did exactly 4 females in each group. And if I randomize again, there's still 4 females in each group. And again, 4 females in each group. And you'll notice the females are always at the bottom because they separated. So first, they randomly assign the men to each group, and then they randomly assign the females to each group, making sure they get 4 in each group. Okay. And every time I randomize, I will always get 4 females in each group, which means the difference in sample proportions will always be 0. And it doesn't matter how many times you do this, it will always be the same. Because we did the block design, we get the same proportions of males and females in every group. So blocking is just a way to make our experiments better. That doesn't mean you have to do it every time. It doesn't mean people do it every time. But if you know you have this confounding factor that would be easy to kind of control for using blocking, it's a great way to get better results. So we always want to randomly assign subjects to groups and experiments. In this class, we're going to assume that we're just like simply randomly assigning subjects to the groups, so we're not doing anything fancy. However, there are a lot of more complicated and complex methods to assign subjects. These complicated methods help us control for confounding variables, but they also require more complicated analysis, which we just can't teach you in this class. So blocking is just one of the possible complex methods to assign subjects. Okay, to summarize blocking, if you know there's a confounding variable, you can separate your subjects into blocks like male and female, old and young, healthy or ill, etc. Then you randomly assign subjects from each block into the two treatment groups. And blocking lets you get exactly the same number of subjects from each block into each of your experimental groups. So you get the same amount of males in each group, or the same amount of old people in each group, etc. And I put here a reminder of association versus causation. So we said two variables are associated if they give us information about each other or if we can find patterns between them. But association usually doesn't mean we can show cause and effect. There are often confounding variables responsible for the apparent association. So for example, this comic said, I wish they don't turn on that seatbelt sign so much. Every time they do, it gets bumpy. So turning on the seatbelt sign is associated with a bumpy flight. Right? They go together, that makes sense. But turning on the seatbelt sign does not cause a bumpy flight. Or for this example, as children's shoe sizes increase, so do their reading skills. So does this prove that foot growth causes reading skills to improve? Obviously not. So it looks like foot size is changing an increase, causing an increase in reading skill, but really age is affecting foot size and age is affecting reading size. And so age is that confounding variable. So age is confounding. So common confounding variables you might see in various studies could be like age, gender, socioeconomic status, diet, exercise, education, genetics, occupation, religion, and so many more. So a few examples. At a recent conference on eating disorders, a research group presented data showing that individuals who undergo a stomach stapling procedure to control their weight tend to have obese children. The researchers concluded that the parents' stomach stapling caused the obesity in their children. Okay, and obviously, we can look at this and say, that doesn't even make sense, right? Okay, like, how does a parent getting their stomach stapled affect their child? But let's look at this. First, what is the explanatory variable? It would be like kind of what groups were they in, or like what maybe treatment were they getting. So in this case, it is whether or not they get their stomach stapled. And what is the response variable? It's like, what are we collecting data on? What are we trying to study? That would be whether or not their children are obese. Can you think of any possible confounding factors that are related to both having a stomach stapling procedure and to having obese children? Okay, well, I'm sure you could think of a lot of them, but if you think about like genetics, okay, so if you have the genetics that cause you to be a little bit heavier, then you might be heavier. You probably get your stomach stapled, but also the same genetics are passed on to your children, so your children also be heavier. So like genetics or diet or lifestyle. So your children often share the same diet and lifestyle. So if your diet and lifestyle are making you heavier, then it'll probably also make your children heavier. Okay. And do you think this was an observational study or a controlled experiment? It didn't give us a lot of info, but do you think they are making people get a stomach stapling procedure? I would guess probably not. So I'm guessing observational study, because I don't think they made people get their stomach stapled or not. I don't think they said, you guys get your stomach stapled and you guys don't, so that we can compare you. This example, when the polio vaccine was invented, they needed to know if it worked. In one study, they randomly assigned children whose parents consented to vaccine and placebo groups. So you can see we had the polio. Well, let's see. So across the rows here, we had, if they got the vaccine, then 56 people got polio. And if they got a vaccine, then 199,994 people did not get polio. And if they had the placebo, then 142 of them got polio, and 199,858 of them did not get polio. So in this case, what would be the explanatory variable? The explanatory variable is whether they get the vaccine or placebo. What is the response variable? The response variable is whether or not they get polio. is this an observational study or a controlled experiment? Okay, did we actually put people in groups? In this case, we put people in groups. So the researchers assign children to the vaccine or placebo groups. So it is an experiment because we assigned them into the different groups. Now let's find some conditional proportions here. So let's look at what proportion of children with the vaccine got polio. So I come up and I only care about people that got the vaccine. So find the either row or column that has the vaccine. And we want to look at what number got polio. So that would be 56 people that got polio out of 200,000 that had the vaccine. And if you put that in your calculator, it's a very small number. So that is 0.00028. And let's see, what proportion of children without the vaccine, so without the vaccine, got polio? So now we come back up and we look at without the vaccine, with the placebo, and there were 142 people that got polio when they were on the placebo out of a total of 200,000 people. So we do 142 divided by 200,000. Gives me 0.00071. Now that might not seem like a huge difference, okay? And a lot of people weren't getting polio, at least in this specific study. But the thing you have to remember is that when people did get polio, it was horrible. People were paralyzed, or people died. No one wanted their kids to get polio. And so if you could go from having like a 2 or 2.8 out of 1,000 chance, or go from a 7 out of 1,000 chance to a 2 out of 1,000 chance, people were very excited about that. And over time, as less and less people got polio because they had the vaccine, eventually we were able to completely eradicate it, and that was amazing. Okay? And so that was a big difference. But now looking at these two proportions, if we look at the proportion for each group, those are different proportions. So when we have different proportions in each group, that means there is an association between getting the vaccine and getting polio. Now we can only say cause and effect if it's a well-designed experiment. Okay. But just looking at the numbers, we can say there's definitely an association. Now, can we say cause and effect? So we can only say cause and effect if we have random assignment to the groups. Okay. If you go back up and look, did we have random assignment? So it says that they randomly assigned children. So yes, we can say cause and effect.